Okay, so hello everyone. First, I'd like to thank the Optima team for the invite to give this seminar. Thank you very much. So as Sean mentioned, I'm going to talk about the optimizing port-hinterland container transportation for resilience and sustainability. So this is actually the title of a research project. A team of researchers from the University of Newcastle and TU Technische Universität Braunschweig in Germany, we were awarded the Australia-Germany Joint Research Cooperation Scheme Fund by Universities Australia and DAD to undertake this one-year collaborative research project. The project started in February this year and it will end in February next year. I am leading this project, and last June, so a couple of months ago, I did a research visit as part of this research project to TU Braunschweig. And on Friday, so in 2 days, a PhD student from TU Braunschweig is coming. She's a member of the team. She's coming to work under my supervision in this research project for almost 2 months. And so I thought it would be nice to present what we have achieved, what we have done in this research project so far. And we submitted, so most of the things that I'm presenting today were included in the Motzing paper that we submitted. It was accepted, so we will be presenting that in Motzing conference down in Adelaide beginning of December, end of November, beginning of December. So I'm here today on behalf of my team to talk a little bit about this research project. So here is what I'm going to cover in this presentation. I will start laying out the context of our study. Then I will present the objectives of our research, followed by the problem definition and proposed solution approach. The computation experiments are broken down into 3 sessions. I will describe the climate change related disruption scenarios, CCD scenarios, and then introduction of the possible immediate recovery actions and computational results. Finally, I will wrap this seminar up with a conclusion and by sharing with you the references I included in this presentation. So, introduction. Container transportation between Australia's seaports and the hinterlands is a critical component of the nation's logistics and trade infrastructure. In 2022-2023, major Australian container ports they handled over a total of 8.6 million 20-foot equivalent units, so TEUs. And this is about 0.33 TEUs per person in Australia, compared to less than half, so 0.15 TEU per person in the US. So the message is Australia is an island nation that heavily relies on maritime trade. These volumes, they were moved across the country via Port-Hinterland container transportation networks, so PHCTNs. And if you don't know, a PHCTN refers to the system of infrastructure that connects a seaport, so the port area, with its hinterland, so the inland region it serves, for the transportation, for the movement of containerized goods. This network includes mainly 3 components: seaports, which are gateways for international maritime trade, where containers are loaded and unloaded from ships, inland terminals or in dry ports, which are logistics hubs located inland that facilitate custom clearance, storage, and intermodal transfers. And the last one is transportation modes, which are rails, road, and barge connections that move containers between seaports and inland destinations. So here on this slide, you can see that I included an illustration of a simple PHCTN with a single seaport. And then we have dry ports, so inland terminals illustrated, represented by yellow dots, and then links connecting those dots, which are transport modes. So we've got rail, road, and alternative links. And can also see the serving areas for those dry ports. Due to the strategic locations, seaports and the hinterland transportation networks are vulnerable to CCD events, so climate change related events. For example, here in Australia, some of you might remember in 2025, so this year, tropical cyclone Zelia forced the closure of one of Australia's largest iron ore port, and this caused major supply chain disruptions. Similarly, in 2022, severe flooding in Brisbane caused disruptions in the Port of Brisbane's operations. That's why it is important to make ports more resilient through CCD. And this means having a clear plan for putting resilience measures into action. However, a study by Becker et al. Published in 2018 found that despite growing awareness of climate change, climate challenges, only a small portion of international ports have actually developed and implemented concrete strategies to build resilience. Additionally, while making PHCTNs more resilient is key to keeping things running during disruption, it is important not to ignore their environmental impact. This is because port-hinterland transport adds a large portion, a large share of CO2 emissions to the overall port logistics chain. And so resilience efforts should also consider environmental sustainability, because it is counterintuitive to try to build resilience in a system whereas you are still contributing to those climate change related events. So building on these observations, we can present the main objectives of our study to introduce the resilient and green PHCTN problem, which is we call RG-PHCTN problem. This is one of the fun parts of optimization. You can create very long names for problems, optimization for new optimization problems, and then you use acronyms to refer to them. Not everyone in the team is happy with this acronym, with this name, but we are going to stick with that until we find a better one. And the second objective is to propose a two-stage hybrid optimization framework. The goal of this new optimization problem, RG-PHCTN, is to optimize container transportation between seaports and their hinterlands by A, enhancing the network's ability to recover from CCD, and B, minimizing CO2 emissions associated with the recovery actions adopted to deal with these CCDs. By implementing the proposed solution approach, we can design a set of environmentally friendlier recovery actions for PHCTNs to deal with CCD events. And I guess most of you are academics, so we know that you probably know that academics, we love to debate definitions. And so I need to tell you what we mean by resilience. Resilience is a term that is its definition varies a lot based on the area of research. So we follow the qualitative definition of resilience proposed by Cheng et al., which describes the resilience of a PHCTN as its ability to maintain cargo flow and restore performance through recovery actions within acceptable time and cost when disrupted by CCD events. So to summarize, I told you that the main goal of our new optimization problem is to optimize resilience while also reducing the emissions associated with the recovery actions that we adopted to improve resilience. So I explained the qualitative definition of resilience that we use, and we also adopt the quantitative definition of a quantitative definition of resilience, which was proposed by Chang and Miller Hooks. And you can see this mathematical expression on this slide. And just to explain how this works, this definition. So in our model, we represent the set of all possible CCD cases by the uppercase Greek letter xi, and each element, each short case xi, corresponds to one sample realization of a disruption type. For example, one instance of flood with specific spatial and intensity parameters. And then in this context, the resilience of PHCTN, which is expressed as a function of xi, short case xi, is defined as the ratio between the total number of containers successively delivered after the disruption and the total demand across all dry ports. So this is the sum of all demand quantities, D sub omega, for every dry port omega in the set W. So essentially, this resilience measures how much of the total demand can still be met after a disruption. And so we want higher values for the resilience. So values close to 1 indicate high resilience. And this means that the network continues to function effectively despite the disruption. To calculate the resilience of a PHCTN, we use a two-stage hybrid approach. It is called two-stage because it consists of two sequential MILP submodels. So the seaport disruption response model, and we refer to this model as submodel 1, and the hinterland disruption response model, and we refer to this one as submodel 2. So submodel 1 focus on the seaport level. It determines which recovery decisions are implemented, and based on that, it calculates the restored throughput capacity of the seaport. Then, given this restored capacity, submodel 2 determines which recovery actions are adopted by hinterland shippers. And based on those decisions, the model calculates the actual container flow arriving at the seaport. And the interaction between these two models is important, and I will explain why later on. We also call this approach hybrid because it combines optimization with simulation. So those two submodels, MILP submodels, are optimization models. And then we use Monte Carlo simulation to generate multiple realizations of each CCD scenario type. And for each realization, we solve both MILP models sequentially. And by repeating this process for all realizations of a given disruption type, we can then calculate the expected resilience of the PHCTN across the entire scenario space. So let's quickly look at those MILP submodels to understand them a bit better. So starting with the seaport disruption response model, which is the first one that we solved in our two-stage approach. So the model objective function aims to minimize the total recovery time at the seaport after a disruption has occurred. And we can break down this objective function into different components. The first term represents the current operation time of the seaport after the disruption, so before any recovery action is taken. The second term captures the time savings achieved by implementing a specific recovery action J, and this variable gamma sub Sj indicates whether the action is selected or not. So this term only contributes if the seaport is damaged and if that recovery action is chosen. The next term adds the implementation time of that recovery action. So it adds how long it actually takes to perform the repair or the recovery action. And the last component, the last term, introduces a penalty for CO2 emissions generated by the selected recovery action. And this weighting factor, lambda sub S, converts these emissions into time equivalent units so that the environmental impact of that recovery action is explicitly incorporated into the objective. And this objective function is subject to a few constraints. So the first ensures that the total cost of the selected recovery action does not exceed the budget available. And the second one shows how this budget is calculated. So instead of using a fixed amount for the budget, this model determines the budget based on the economic loss caused by the disruption. So this essentially means that the more cargo the port fails to deliver, the larger the recovery budget becomes. The third constraint ensures that only one recovery action can be selected. And the last one defines the nature of the decision variables. So each gamma sub Sj can only take a value of 1 or 0. 1 if the action is chosen and 0 if it's not. So now that we covered this first stage, how the seaport reacts to a disruption, we can move to the second stage of the framework, the second submodel, the hinterland disruption response model. The objective function of this model aims to minimize the total costs incurred by hinterland shippers in response to a given disruption scenario. And these total costs include three components: recovery implementation costs. So this is the direct cost of carrying out recovery actions at the dry port or along transportation links. A penalty for unsatisfied demand. So this represents the economic loss when some containers cannot be delivered to the seaport. And a cost equivalent penalty for CO2 emissions. So this accounts for the environmental impact of the chosen recovery action. And this objective function is subject to a few constraints. So constraint 8 defines the container flow variable F sub omega of xi. So this constraint ensures that flows in the network remain physically feasible. Constraint 9 imposes a maximum delivery time limit. So it ensures that the total transport and handling time does not exceed predefined threshold. Constraint 10 makes sure that only one recovery action can be chosen for each dry port. Constraint 11 defines the recovery decision variable as binary, and constraint 12 ensures that the container flow variable is non-negative. So now that I've covered these two submodels, we can look at how the interaction between the two is relevant, is important. These two submodels, they come together to calculate the total container flow. So the total container flow, the flow everything that is flowing from shippers, hinterland shippers to seaports under a given disruption scenario, she is denoted by TF of she and is expressly mathematically expressed by the equation you can see in this slide. And it is defined as the minimum between two quantities. The total volume of containers that hinterland shippers are able to dispatch. So this comes from submodel 2, and the total handling capacity that the seaport can provide after implementing the chosen recovery action. And this comes from submodel 1. Taking the minimum between of these two values ensures that the two-stage approach respects system level bottlenecks. And what do I mean by that? If the seaport recovers slowly, it becomes the limiting factor. So the capacity, the restored capacity of the seaport is the limiting factor. On the other hand, if the hinterland suffers heavier damage, if that capacity is restored capacity is smaller, the inland side becomes the bottleneck. And once we know the total container flow, so what the demand that is actually met after disruption scenario occurs, we can then calculate the resilience using the formula introduced earlier. So now moving to the computational experiment. So what do we get when we apply the two-stage solution approach to a PHCTN? To find that out, we created a synthetic network inspired by the Port of Newcastle in New South Wales. So this network includes the seaport itself and 3 inland dry ports that represent hinterland terminals. We assume that the network is fully connected, so every node pair is linked by transportation options. At the start of the analysis, all links are assumed to operate at 100% capacity, and this represents the baseline with no pre-existing disruptions. For simplicity, the layout is constructed using Euclidean distances between nodes, and we do that to approximate transportation costs. And so overall, this setup, we believe that this setup provides a control yet realistic environment to get the computational results. We investigate the performance of the designed network under specific CCD scenario types. We focus on the Australian context and design 3 disruption scenarios, flooding, cyclone, and bushfire. These scenarios are based on what Sims and Cannondale explain in an article for The Conversation about climate change impact in Australia. To design the scenarios, we follow Nair and others' framework, where each scenario is defined by a location, an epicenter, severity, and a network impact. Disruptions are modeled probabilistic due to their uncertainty, and disruption effects are represented as capacity reductions in longer operation times, and we do that to reflect the loss in efficiency that the network suffers after a disruption happens. And the disruption scenarios are computed based on those Euclidean distances between the epicenter and network elements by applying the respective capacity loss factors. So what do these CCD scenario types look like? Each scenario has 2 different impact zones. In the flooding scenario, in the first buffer, first zone, all roads and railways within 400 meters of the epicenter are fully unusable. Dry ports are closed and seaport capacity drops by up to 75%. And operating times gets up to 8 times longer when this happens. In the second zone, in the 400 to 1 kilometer buffer, routes and dry ports operate at reduced capacity, and the seaport faces minor disruptions with delays up to 3 times the baseline. Cyclone disruption affects a wider area. So within 800 meters, all routes are unusable. Dry ports are closed and the seaport operates at 50 to 70% capacity with long delays. And in the second zone, between 800 meters and 2 kilometers, transport and dry port capacity drops to 30 to 70%. And the seaport experienced moderate delays and minor capacity loss. In the bushfires, they have intense but local impacts. And in the first zone within 200 meters, routes are unusable. Dry ports are closed and the seaport loses up to 75% capacity. And in the 200 to 700 meter zone, capacity drops are moderate across all infrastructure. And the delays in that zone, they range from 1.5 to 4 times the usual operation time. So the chosen values, they are synthetic, but they intend to reflect relative disruption scales, and we designed those to enable meaningful testing of our models. Once the 3 disruption scenarios are defined, the next step was to identify short-term recovery actions that could be used by seaport operators, so could be used in submodel 1, and by hinterland shippers in submodel 2. There are 2 actions, so we selected 2 actions, 2 actions for seaport operators and 3 for hinterland shippers. Each recovery action is defined by 5 key attributes, and you can see them in this table. So the first one is the recovery capacity of damaged facilities. So this shows the percentage of baseline seaport or dry port capacity restored. Then we have recovered operation time. This attribute shows the percentage of the baseline operation time once the action is implemented. We have implementation time, of course, so this is the time required to implement the action. And it is expressed as a percentage of the baseline operational time. Implementation costs, for sure, everything costs something. So this is the cost of implementing a recovery action, and estimated CO2 emissions. So this is how we assess the environmental impact of each recovery action. And we adopt the recovery actions and their attributes from Chang et al., but we added CO2 emissions to each action because we wanted to have this environmental measure for each recovery action. So in this table, you can see the attribute values for recovery actions. So recovery action S1, so for seaports, so S1, this recovery action uses existing backup equipment to resume operations quickly, and it has implementation time of 50% of operation time. It restores capacity, 60% of seaport capacity, and it runs at 167% of normal processing time. So there is a speed gain here. while it requires prior investment because we have to have idle equipment to be able to implement this recovery action, it costs us around 310 to implement, and it has low environmental impact. The second recovery action for seaports is temporary repair. So this involves repairing damaged equipment. It takes longer to implement this recovery action, 150% of operation time, but restores 80% of port capacity with improved operation speed. The cost is higher at 690,000, and emissions are moderate, as this action involves some type of construction. The first recovery action for hinterland shippers, H1, reroutes containers via a nearby dry port and rail shuttle. The recovery capacity depends on the remaining capacity of the dry port and rail link, and operational time is inversely related to that available capacity. This is to show that, so you can see that the cells are grayed out. So this is to show that they depend on the specific disruption scenario and the available infrastructure after disruption happens. There is no added transportation costs, but shippers must wait while the alternative dry port handles its own demand, and that's the implementation time. Emissions are medium, as rail is generally a low emission. The next recovery action, in the next one, containers are transported directly by road, and this provides a quick implementation time. The recovered capacity on the route can be increased by a huge amount because we assume that all the nodes in the network are linked, but it depends on real world data from Google Maps. It fully restores capacity of dry ports, but at a higher cost, so higher than rail and higher environmental impact. And the cost depends on how many containers are shipped using road transport. And in the last one, H3, shippers choose to wait until damaged facilities are temporarily repaired. So this option takes the longest to implement, 100% of operational time, and it restores 80% of capacity of dry ports and routes. There is no operational speed gain. This is because operations just go back to normal once the facilities are temporarily repaired, and it has no direct costs and emissions, but delays are significant. So those are the recovery actions that we adopted. And what are the results we obtain when we apply our solution approach, a two-stage hybrid solution approach, to this synthetic PHCTN? To assess the performance of each recovery strategy, we use 300 samples for each scenario type, so each flooding, cyclone, and bushfire. And then we computed the resilience, the expected resilience and mean CO2 emissions across all samples of the same type, same scenario type. You can see the computational results on this table here, and the recovery action selection frequencies, they illustrate how often each recovery action is selected by the seaport and by hinterland shippers. So these frequencies, they show how the network adapts to each disruption type. You can see that seaport recovery option S2 was chosen in 100% of cases. So this highlights its central role in restoring capacity. And on the hinterland side, H2 was selected consistently across bushfire and flooding scenarios, and in most cases, 95% of cases of cyclone cases. And H1 appeared only under cyclones. Um, this repeated selection of the same actions across scenarios points to a limitation of our study. We believe that the current set of recovery actions might be too narrow or idealized, and so we need to expand the action catalog to better reflect real-world constraints and trade-offs. In terms of resilience, the approach was able to restore almost full capacities using the selected recovery actions. And bushfires had an expected resilience of 0.93, followed by flooding and cyclone with expected resilience of 0.82. So bushfires, which were characterized by localized impacts and small disruption radius, they led to the highest mean resilience compared to flooding and cyclones. So this was expected. Because this suggests that the spatial extent of a disruption has a greater influence on overall network resilience than the intensity parameters alone. And this also affects the mean CO2 emissions. We can see that although flooding and bushfire scenarios led to the same selection of recovery actions, the mean CO2 emissions of the flooding scenario was actually higher. We believe that this was because the more recovery actions were needed for dealing with the flooding related events, as flooding feature a larger spatial extent than bushfires. To conclude our experiments on a synthetic Australian PHCTN show that the proposed framework produces plausible and interpretable results in terms of resilience, CO2 emissions, and recovery strategies. And so these findings, they demonstrate the strategic value of the approach for supporting decision-making in PHCTNs to deal with climate change CCD events. One of the key strengths of the framework is its modular and flexible design. This means that we can easily adapt the recovery actions, the cost factors, emission coefficients. A lot of things can be changed in this framework and can be changed based on infrastructure in different contexts. Also, the sequential MILP structure ensures transparency and scalability. We can the features, so the objective constraints and network features, they can be integrated different objectives, constraints. They can be integrated without redesigning the entire models. But it is important to note that the current disruption scenarios and results are based on stylized synthetic data. And this was because we just wanted to illustrate, to show that the methodology works, and we could do that because actually real-world climate events such as bushfires and flooding, and that was one of the feedback that we got from Modsing reviewers, is that those events, they tend to cover much larger regions and last longer periods. And so our numerical results, they should be viewed as illustrative demonstrations, not as precise forecasts. And looking ahead, as usual, we plan to expand the recovery action set, the two sets. And we also plan to replace the synthetic network with data derived from open street map. And we also want to conduct sensitivity analysis to better understand how the disruption radius, the intensity of the disruption influence the resilience indexed. That's also, those are the references that I included in my presentation. Thank you for joining this seminar. Thank you for taking the time to listen my research.